Hey everyone, we're surrounded by these incredible structures every single day, right? Bridges, stadiums, skyscrapers that just seem to defy gravity. But have you ever really stopped and wondered what is actually holding them up? Well, that's what we're going to dive deep into today. We're going to explore the absolute heart of structural engineering, the column, and the four critical ways it can fail.
I mean, really think about it. What stops a 100-story building from just collapsing? It's a pretty simple question, but the answer is incredibly complex. See, when you're dealing with forces that massive, it's not just about being strong. It's about being smart. It's about anticipating every single thing that could possibly go wrong. The secret isn't just brute strength. It's a deep, deep understanding of weakness.
And this quote right here, this is the single best way to think about it. Imagine an engineer isn't just a builder. They're an expert defensive driver. They don't just know how to hit the gas and go forward, they know every single type of crash that could ever happen, and more importantly, exactly how to avoid it. This analogy is going to be our guide for this whole explainer.
Okay, so to understand the crashes, we first have to understand our car, the column itself. And here's the first thing you have to get your head around in structural engineering. In the real world, there is no such thing as a perfect part. Every single piece of steel has these tiny, unavoidable flaws that an engineer must account for.
It all starts with how the column is even made. A hot-rolled steel section, which is formed from liquid metal, is kind of like a unibody car frame. It's generally stronger, thicker, all one piece. On the other hand, you have cold-formed or built-up sections, which are made from thinner sheets of steel that are welded or bent into shape. Now, they can be super effective, but that thinner nature, that introduces a whole different set of risks, which we are definitely going to see in a minute.
So, imperfection number one, no column is ever perfectly straight. It's impossible. In fact, design codes actually allow for a tiny bit of wiggle room, a curve of about its length divided by 1,000. So think about it. A 10-meter column can be a full 10 millimeters out of whack. Now, that sounds tiny, right? But that little curve means the load from above isn't perfectly centered. And that creates these nasty secondary forces, like bending or twisting, that can be incredibly dangerous.
The second hidden flaw is something called residual stress. This is fascinating. So when they make a steel I-beam, the fin tips of the flanges, they cool down and harden first. But the thicker part, where the web and the flange meet, that cools down last. Well, this uneven cooling literally locks stress into the steel. The tips are already squeezed in compression, and the junction is being pulled in tension, all before a single bit of load is even put on it. It's wild.
So you've got these imperfect parts, right? They've got hidden stresses, they're never perfectly straight. How on earth do engineers guarantee safety? Well, they go back to being defensive drivers. They follow a super strict rulebook that's been designed to anticipate every single potential problem they could ever face on the road. And this is the real game changer in how you have to think about this. A great engineer doesn't just ask, hey, is this column strong enough? No. They ask, what are all the different ways this specific column could fail? And have I, without a doubt, prevented every single one of them? It's a total mental shift from just building something strong to building something that's defensively, comprehensively safe. All right, so let's get into the nitty-gritty. Let's talk about those crashes. Our source material lays out 4 primary ways a structural column can fail, and a truly safe design has to be checked against all 4 of them. Here they are, they're 4 big ones. You've got yielding, overall flexural buckling, local buckling, and torsional buckling. Each one is its own unique kind of disaster, and each one tends to affect different types of columns. So let's break them down one by one. First up, we have yielding. This is the crush failure. It's probably the most straightforward one to imagine. Think of a really short, stubby column, like a little concrete pedestal. If you put way too much weight on it, it's not going to bend or twist. The steel itself is just going to squash permanently. Its resistance is pretty much just its cross-sectional area times the material's yield strength. Simple, direct, and brutal.
The second one, and this is a really common one, is flexural buckling. This is the swerve. It happens to columns that are more slender or long. Instead of crushing under the load, the whole column just suddenly kicks out and bows to the side. The risk of this happening is all about its length, its shape, and crucially, how it's being held in place at the top and bottom.
And that brings us to this number, 200. This is a hard and fast limit right out of the engineer's rulebook. It represents the maximum slenderness ratio a column is allowed to have. Think of it like a non-negotiable speed limit.
If your column slenderness is over 200, the risk of a sudden swerve failure becomes way too high. Doesn't matter how strong the steel is, you're in the danger zone. Period.
Third on our list is local buckling. Let's call this the dented panel. Now remember those thinner, cold-formed columns we talked about? This is their Achilles heel. In these sections, known as Class 4, before the entire column has a chance to buckle, one of its thin little parts, like the flange of an I-beam, can actually ripple or buckle all on its own, just because it's too thin for its width.
And finally, our fourth failure mode is the spin-out, torsional buckling. This is where the column literally twists under the load. And it's not just one type of spin-out either. For a perfectly symmetrical shape, like an I-beam, it might just do a pure twist. But for a shape that's only symmetric one way, like a C-channel, it can do something even more complex. It can twist and bend at the exact same time. That's called torsional flexural buckling. So let's just step back and put it all together. You can see a really clear pattern here, right? You've got the crush for the short, stocky columns. You have the sideways bow for the long, slender columns. You get the dented panel for the ones with thin walls, and you have the twist for columns with very specific shapes. Each crash is a completely different physical event that the engineer absolutely has to check for. So this brings us right back to our central idea. The engineer, acting as that defensive driver, has now identified all the potential crashes. So the final step is to make sure their design, their blueprint for the road ahead, safely and confidently navigates around every single one of them. And this right here is the ultimate takeaway. Look, a column isn't safe just because it won't get crushed. That's not enough. It also has to be proven through calculation that it won't bow, that its thin panels won't dent, and that it won't twist. Safety isn't just one check mark. It is a comprehensive process of eliminating every single known risk. So, the next time you walk through a city and you look up at the raw steel skeleton of a building rising into the sky, maybe you'll see it a little differently. Not just as a collection of strong beams, but as an absolute masterclass in defensive design, a system engineered to perfection against every single possible way it could fail. It kind of changes things, doesn't it?